Hello guys. Good morning. Good morning to all of you. Today in this session we'll be discussing about WKB approximation. You know, WKB approximation is one of the most important topics and very easy topic. You just need to remember few formulae, and if you know integration, then you can go for this problem. And WKB approximation may give you one question in the part C, maybe hopefully in the part C, 5 marks. And once you learn it, you can easily solve question, and very easy topic. So without any further ado, I hope everything is all right, audio, video, everything. So without any further ado, let's start. Good morning, Murli. Okay, so let us start with WKB approximation. You see, when do you use WKB approximation? Look, when we know exact Hamiltonian, we use Schrodinger equation to get the solution. Then we got the perturbative approach. Perturbative approach, when the exact Hamiltonian is slightly disturbed by some perturbation. Then we have variational method. So here we take, here the Hamiltonian is far away from the exact Hamiltonian. Here what you do, here in variational method we take a trial wave function and we find the ground state, okay, minimum ground state energy. So for this was useful. Now another approximation method is WKB approximation method. Now what is the speciality of WKB approximator? When do you require to use this? WKB is used when the potential V of x changes slowly over distances comparable to the de Broglie wavelength. So the variation of the potential will be very slow. So in those cases, WKB approximation will be useful. It is not valid near turning points when E is equals to Vx. To remember this one. Now we can consider that the energy of the particle, it may be more than V of x, less than V of x, and equal to V of x. So if I consider the first case, case 1, E greater than V of x, this is known as the classically allowed region. Okay. So you can imagine it in this way, the potential is slowly varying. It is delimited by some turning points x1 and x2. So when E greater than V of x, this is known as the classically allowed region. For this case, if you consider the Schrodinger equation, d square psi by dx square plus k square psi equals to 0. But we have done it so many times, right? When E greater than V, so k will come square root of twice m E minus Vx by h cut square, if you keep it this h cut under root. Okay, and for such cases your general solution becomes psi of x is equals to a by square root of k to the power plus minus I integration k dx. Okay, so this represents, you can know, e to the power plus minus I kx. So this is oscillatory in nature, sin x cos x, in terms of that you will get the solution. So it is oscillatory in nature. So this represents an oscillatory behavior as expected in the classically allowed region. Okay, so these are just formality. What we need to know from WKB approximation, we need to know about 3 formulas, okay, which I will be discussing, and based on those formulae you are good to go for the problem. I am just giving you a little bit of theoretical part, that when E less than Vx, you get classically forbidden region and you get the solution in this way. We have done it many times, d square psi by dx square minus gamma square psi is equals to 0. Here it will, instead of E minus Vx, it will now become V minus E, because E is less than Vx. And for this case the general solution will take the form B by square root of gamma e to the power plus minus gamma dx. So this is, you can see this is not oscillatory in nature. This gives you exponential decay e to the power minus this thing, or growing solution to the power plus this thing, typical for tunneling. Now case 3, this is interesting. E approximately equal to Vx near the turning point, where the particle is coming momentarily at rest, then E approximately equals to V of x at these classical turning points. So whenever you want to find out the classical turning points, you need to equate the energy equals to V of x, means kinetic energy becomes 0. So for this case, if you consider E equals to Vx, you see Vx minus E, or here E minus Vx, all of them will be 0. So K will be approaching to 0, and as well as this gamma is also approaching to 0. The wave function becomes undefined, WKB breaks down here. That is why we said it is not valid near turning points. Turning points are the points where E is equals to Vx. This is most important thing to note. Turning points are points where E is equals to V of x. Now let me give you the 3 rules which you require in WKB approximation. WKB approximation rules for bound state energy. Now as I have shown you, this is delimited by 2 walls. Now depending on the nature of these walls, will have different formulae. If both walls are smooth, so if you represent it in the form of the potential, you can represent it in this way. So we have the potential V of x versus x. So both walls are smooth. What does it mean? There is no rigid boundaries. If we consider, let's say, we have a potential of this form. We have a potential of this form. Like this. So how do you get the classical turning points? For this case, let's say the energy of the particle is E. Energy of the particle is E. So obviously it is cutting at this point and this point. This point is x1, point is x2. So we can see 3 regions. One is this region, another one is this region, another one is this region. So this is the example of potential with no rigid wall, means both walls are smooth. This is the example of potential with no rigid wall. Now what about region 1? Region 1 and 3. These 2 regions are classically forbidden. Classically forbidden, while region 2 is classically allowed. Okay. So for this case, if both walls are smooth, for this case we use this integration x1 to x2 px dx is equals to n plus half pi h cut. Look, whenever you have to write n from 0, then you are going to use this formula 0, 1, 2, 3 and so on. Look, x1 and x2 are classical turning points where E becomes equals to V of x. and as you can see here E and Vx becomes equal. So you see n plus half pi h cut when n starts from 0, 1. Now you want to start the variable from n from 1. What you gonna do? N will be n should be increased by 1 unit. Okay, so this can also be alternatively written as n plus 1. So whenever you see n, you will add n plus 1. So plus half. This 1 was not there, so we are subtracting that 1 minus 1 pi h cut. Now we just replace this variable n plus 1 by m, and we get it x1 to x2 m minus half pi h cut. Where m is equals to, instead of 0, 1, 2, 3, we will start from 1, 2, 3. Now in your question, depending on whether you need to start from 0, 1, 2, 3, you will use this formula, or if it starts from 1, 2, 3, you can use this formula. Look, m and n doesn't matter, okay, because here just to make it different we have used two variables n and m, but whenever you will be dealing with questions, you have to see whether it is starting from 1 or starting from 0. If it is starting from 0, you will use, let's say, n plus half pi h cut. If it is starting from 1, you will use n minus half pi h cut. Okay, so this is the case where if both walls are smooth. Now let's go for the second case. Is there any question from this? If one wall is smooth and the other wall is rigid. Now this is this thing, how will you represent pictorially? Pictorially, if you want to represent this, we can consider a potential like this. Let's say we have this potential versus x graph, v of x versus x. Now one of the walls is rigid, another one is smooth. So how will you draw this? One example. So you may draw it like this. Maybe like this. So you see it is cutting at only one point. This is x1. This is your x1. And here this will be x2. And this is the E value. So this is the case of potential well with one rigid wall located at x is equals to x1. Okay. So for this case, how this formula gonna change? So we have also here the classical turning points x1, x2. So for this case, the formula will take the form integration x1 to x2 px is the momentum, dx is equals to, it will be n plus 3 by 4 pi h. We do not need to do this proof. You just need to remember the formula. N plus 3 by 4 pi h cut, where n starts from 0, 1, 2, 3 and so on. Now let's say if this n doesn't start from 0, it starts from 1. So as I told you, what we have to do, we have to replace n plus 1 by m. Okay, so to do that, what you gonna do, look, so for the time being you just replace n by n plus 1. So plus 1 we have taken extra, so we have to subtract y by x. Next task, you replace n plus 1 by m. So this is equals to m 3 by 4 minus 1, so minus 1 by 4, m minus 1 by 4 I h car, and here you will start the value of m to be 1, 2, 3, 4 and so on. Depending on whether it is starting from 0 or 1, you will use the formula. Now another formula is there. So we considered two possibilities, both wall are smooth, one wall is smooth, another wall is rigid. Now the third case may be both walls are rigid. If both walls are rigid, for this case, what you gonna have? So let's consider the potential for this case. Both walls are rigid, so you can imagine it in this way. We have this potential with both walls, both rigid walls. This is one of the rigid walls, another rigid wall, and we are plotting, let's say, v of x versus x. And the potential, let's say, varying like this. Okay, this is the value of energy. Energy E, this is x1 and this is x2. Okay, so this is about potential well with two rigid walls located at x1 and x2. So for this case, what you gonna have? Integration x1 to x2 px dx is equals to, the formula is n plus 1 times I, where your n start from 0, 1, 2, 3 and so on. So obviously if you want to write it in this way, n, okay, so this is so straightforward, you do not even need, we can directly write it as m pi, because already it is n plus 1 equals to 8. So if you start from 1, 2, 3 and so on. Is everything clear? So you have to identify whether the what is the nature of the potential, whether both walls are smooth, if one wall is smooth, if another wall is smooth. And regarding this px, you know how to calculate px. Some additional note I'd like to give you here. Look, you know the energy, total energy is 2 p square by 2m, let's say, plus v of x, right? So p square by 2m, so p square is equals to, you see, twice m times e minus vx, right? So from this we can write p. If I am writing v of x, so let's say this is px square, so px square. So if I write px, it is square root of twice m E minus V of x. So if I take let's say the positive value, you will get this one. So this P you can replace here depending on the situation, and by putting the limits and equating it to this right hand side, you will get the answer. You can find out the energy again, energies, okay, energy of different states. Is it clear? Let's move on. Let's solve some problem, then it will be more clear to you. Consider a particle of mass m in the potential V of x is equals to a mod x, where a greater than 0. The energy eigenvalues n equals to 0, 1, 2 in the WKB approximation. So using this WKB approximation, we find energy eigenvalues. Okay, can you do this problem? So here the given potential is V of x is equals to a mod x, energy eigenvalues in the WKB approximation. So what you require if you want to apply the WKB approximation? We require these classical turning points x1, x2. Okay, we need P. So P we can easily find out using this formula. So let's try to do this. What is given? Given V of x is equals to a mod x, where a greater than 0. So first of all, we need to visualize this potential. Okay, so if you draw this potential, you know how it will look. V of x versus x, a mod x. So if you consider V of x, a mod x means what? Ax when your x greater than 0. This is minus x when your x less than 0. This is what we have, right? So Ax is a straight line with positive slope like this. Minus Ax, it is also a straight line, but it with negative slope and passing through the origin. Y goes to mx plus c, c goes to 0 here. So on the negative side it is like this. Now what we have to do? We have to take the energy values. Okay, let's say the energy is this. So it is cutting at 2 points, x1 and x2. Okay, x1, x2. So what will be the values of x1 and x2? Look, at classical turning points, E equals to Vx. Okay, so we can say E equals to a mod x, and from mod x is equals to E by a, and that is why x is equals to plus E by a. Let's say one value is plus E by a, another value is, okay, so x1 we are writing minus E by a, x2 is equals to plus E by a, okay, because x can take two values. So what two values, at what two values E is equals to a mod x? So you can see it is at one value here at x2, and at x1 this criteria is satisfied. So obviously this x1 is minus E by a and x2 is plus E by a. I hope this is clear. So as per W, and what kind of wall is this? What kind of wall is this? And you see n is equals to 0, 1, 2, 3. So it is starting from 0. What kind of wall is this? This is the first case, na? Both walls are smooth. It is not like there are rigid walls. These walls are smooth. Understood why it is the first case? It is the case of the potential where both walls are smooth. So according to WKB approximation, what we can write? According to WKB approximation, we have x1 to x2 px dx is equals to n plus half pi h cut, where n starts from 0, 1, 2, 3. So you have to remember which formula you are going to use. So you do not need to remember all these 6 formula. You can just need the first formula, maybe n starting from 0. And if you see somehow that if it gives you that n starts from 1, then you can just directly put n plus 1. So you have taken plus 1 extra, minus, do minus, then replace n plus 1 by m, and you will get the formula. So just remember the formula with n equals to 0. Now what is p? We have already told you, square root of x1 is minus e by a, x2 is plus e by a, p is equals to square root of twice m e minus vx. Vx is this a mod x, right? Dx is equals to n plus half times pi h cut. Now you see, when you put the value of x less than 0, then this will become square root of twice m e minus plus ax dx. Or if you look at closely, e minus ax, this is an even function, right? This integrand is an even function. If you put x equals to plus minus x, this value remains same. So we can write 2 times 0 to e by a twice m e minus x by taking the positive values of x. This is equals to n plus half pi h cut. Clear? Now what we need to do, let's take this term inside the square root, twice m e minus ax is equals to t. Okay, so minus twice m a dx is equals to dt, or dx is equals to minus 1 by twice m a dt. Let's change the integration limit. The limits for x was 0 to e by a. So if you put x is equals to 0 here, t becomes twice m e, and if you put x equals to e by a, t becomes 0. Okay. So what you get, therefore 2 times 0 to e by a becomes twice m e to 0, square root of t, dx is minus 1 by twice m a dt. This is equals to, the right hand side remains same, n plus half pi h cut. Okay. So this is equals to minus 1 by m a, Acha, if you take this limit to be 0 to twice me, this minus is absorbed. So 1 upon 2 get cancelled, 1 upon ma, 0 to twice me, t to the power half dt n plus half pi h cut, 1 upon ma, t to the power 3 by 2 by 3 by 2, 0 to twice me, n plus half pi h cut. Getting going along with the calculation. So this is equals to 2 by thrice ma twice me to the power 3 by 2. This is equals to n plus half pi h cut. And that makes e to the power 3 by 2 is equals to twice m to the power 3 by 2 is there. So what we can write? 3a pi h cut, 3a pi h cut divided by, look, 2 into 2 to the power 3 by 2. So 2 into 2 1, okay. So 2 into 2 4, and we have square root of 2 and square root of m. So 4 square root of 2m into n plus half was there. So let's keep it that way. So E is equals to how much? 3a pi h cut upon 4 square root of 2m n plus half to the power 3 by 2. So if you want to remove it, we have to make it 2 by 3, and hence we can finally write En is equals to 3a pi h cut by 4 square root of 2m n plus half to the power 2 by 3. N starts from 0, 1, 2, 3 and so on, and that is matching with option B. Is the solution is smooth like this, like the walls, or any question? You just need this integration skill, the rest will follow automatically. Let's go for another problem. What do you say? The nth energy eigenvalues En of a one-dimensional Hamiltonian. Look, h equals to p square by 2m plus lambda x to the power 4, where lambda is a constant. In the WEB approximation is proportional to. Sometimes WKB approximation is also known as WEB. Will you give it a try? What is given? H or E? P square by 2m plus lambda x to the power 4. This is given to you. Now what formula you are going to use here? Lambda x to the power 4, this is not the this is not like okay, so this is like both also are smooth, right? And in this problem, you see there is no mention of whether n starts from 0 or 1. So how will you choose? Look, n plus half is there. Along with this formula, where is n plus half is there? In the first formula itself. Other than the first formula, there is no formula like n plus half. So by looking at the option, we can say that we have to use the concept of both also are smooth. Okay, and from the potential also we can imagine. So v of x is equals to lambda x to the power 4. Lambda into x to the power 4. Just give me a moment. Let me just check the graph for yeah, if you consider this graph of lambda x to the power 4, you can see this kind of graph we get. Look, you can easily imagine, look, half kx square harmonic oscillator potential, you get a parabola like this. Okay. Now, as the power of x gets increased, so x cube will be an odd function, it will also extend like this, but for even functions it will getting flat and flat. So from this we can also consider like this. This is v of x, this is x. So obviously these 2 points will give you the turning points, this and this. Okay. x1, x2. So what will be the value of x1 and x2? So we need to make it equal to E. So for the classical turning points, E approximately equals to Vx. So E is equals to lambda x to the power 4. From this, x to the power 4 is equals to E by lambda. And obviously you can say that the value of x1 and x2 are plus minus E by lambda to the power 1 by 4. Okay. E by lambda to the power 1 by 4. Therefore, by using WKB approximation, we get, let's say, minus, okay, let's write the formula first. Is this okay? Therefore, x1 minus e by lambda plus p is equals to square root of twice m e minus vx, so lambda to x to the power 4 dx n plus half pi h cut. So here also this is an even function, so twice me, square root of twice me you can take outside with along with 2, so this becomes 0 to e by lambda to the power 1 by 4, and what you are left with, integration 1 minus lambda x to the power 4 by e dx. The good thing is we do not need to carry out the integration completely. It is asking you what is this proportional to. Okay, so even without calculating the integration, we can say the dependency of energy on these quantum numbers. Okay, so let, for this case, maybe lambda by e to the power 1 by 4 time x is equals to, let's say, u. So we can say dx is equals to e by lambda times 1 by 4 times du. And if you change the limit, then we can change the limit like this. The limit of x are 0 and e by lambda to the power 1 by 4. On the other hand, if you consider the value of u, x is equals to 0, so it is 0. For x is equals to e by lambda to the power 1 by 4, it is 1. Okay, so you can say that 2 into square root of twice me integration 0 to 1 square root of 1 minus u to the power 4, okay, dx is du, and you see, let's keep it here, and this e by lambda to the power 1 by 4 we are taking out of the integration, n plus half pi h cut. Now as you can see, this part inside the bracket 0 to 1 it is the square root of 1 minus e to the power 4 du, this will give you a number, okay, which is not depending on e. This term is independent of e, because this is a simple integration, you see, some number you will get. So one dependency you are getting from of e, from here it is half, e to the power half, and square root of twice m to everything will absorb in the constant. This is also constant, and e to the power 1 by 4, so plus 1 by 4. Other things are absorbed, okay. So we can write proportional to n plus half times pi h cut. Okay, let's keep this contribution of lambda to the power 1 by 4. Lambda value is given in the question. If it gives lambda value is also given, so we have to take lambda also, and others, let's say this square root of twice m 2 and these things are absorbed in the proportionality constant. Okay, so you can see e to the power half plus 1 by 4 is equals to 3 by 4. E to the power 3 by 4 is proportional to n plus half into pi h cut to the power lambda by 4. 1 by 4, and hence your energy E is proportional to n plus half to the power 4 by 3, okay, lambda to the power, we have multiplied with 4 by 3, so 1 by 3, and this is matching with the pi h cat is also absorbed. A. Clear? Let's do this problem. This is the last problem we will be doing from WKB approximation in this class. Consider the quantum mechanical analog to the classical problem of a ball of mass m bouncing elastically on the floor under gravity. So it is like one of the walls is rigid, another wall is smooth, isn't it? You can see the ball will hit here and it will come back again, it will go back again, it will hit and jump, hit and jump. So you see it is a rigid wall, and when it is in the air it is like smooth, okay. So it is bouncing elastically on the floor under the gravity G, z cap. For negative z, potential energy is infinity. So this is your z is equals to 0. For negative z, the potential will be infinity. Energy En can be found by WKB approximation. If En cube is equals to this, then you can see n is equals to 1, 2, 3. Remember this one, which formula you need to use, the value of alpha. So you have to use when the one of the walls is rigid, another one is smooth, and n starts from 1, 2, 3. So second formula we have to use, okay. So we have to use m minus 1 by 4 pi h cut, because you can see it is starting from 1. So let's do this. So you can see the minimum value, look, the classical point here it is z equals to 0, another at maybe any value z is equals to z, okay. So two classical turning points are, you can say 0 and z. And here what is the potential energy? The potential here is given by so you can see it is V of, let's say, z, this is equals to mgz. If the mass of this ball is m, so potential energy will be mgz, mgh formula. Therefore, and the classical turning points are x1 is equals to 0. So here it is, instead of taking x1 x2 we are writing z1. Okay, here the coordinate which you like to take is not x but z. So z1 is equals to 0 and z2 is equals to some z. I hope this is clear till now. So therefore En, by using WKB approximation, we can write okay, we need to calculate En, so we will calculate En. Now we can use, using the WKB approximation, what do we get? We get integration x1, so x1 will be replaced by z1 to z2, let's say square root of, or let's write the formula, original formula, that is pz dz. This will be equals to n minus half, sorry, 1 by 4 pi h cut, where n starts from 1, 2, 3 and so on. Can I write it? So let's put the values 0 to z. P is equals to square root of twice m e minus v, that is mg z dz equals to n minus 1 by 4 pi h cut. Again we are going to take square root of twice m e common. Acha, this z value we can calculate, right? z1 is not z actually. Look, if we make for turning points, we have to make E approximately V of z, that is mgz, or z is equals to E by mg. So this will be E by mg. Okay, E upon mg, E upon mg square root of 1 minus mgz by E dz. Now it's look good. Again the same strategy we are going to use. Let 1 minus mgz by E is equals to t, changing of variable. So dz is equals to minus E by mg dt, right? Let's change the variable. The variable of for z is 0 and E by mg. The variable for t, for z equals to 0 it is 1, for z is equals to E by mg it is 0, and hence we can write here. We need to actually solve the integration, so this will make our calculation a little bit difficult, but we are pro, we can easily calculate the square root of twice me integration 0 to E by mg, so it becomes 1 to 0, 1 to 0. T to the power half dz. Okay, let's keep this thing and this minus E by mg outside, n minus 1 by 4 pi h cut. Now if we absorb this minus sign, it will become, look, square root of twice me into e square square root of 2 by m, na? 2 by m e to the power half plus 1, 3 by 2. Here it is 0 to 1, t to the power half dt n minus 1 by 4 pi h cut. Okay. So let's keep it as it is. Now integration of t to the power 3 by 2 by 3 by 2, 0 to 1, n minus 1 by 4 pi h cut. Next, what you're gonna do, if you put t equals to 1, you get, let's say, square root of twice by m e to the power half into 1 by 3 by 2, so 2 by 3. This is equals to n minus 1 by 4 pi h cut. G is somehow missing. G is where? We have neglected G. So let's write 1 by G here. 1 by G. 2 by 3G. Is it correct, or is there any mistake again? So e to the power half is equals to 3g by the root over m by 2 root 2 n minus 1 by 4 pi h cut. Just check whether I have written everything or not. Have I left anything? So you have to take a square to make it e. So 9, 2 root 2, 4 into 2, 8, 9 by 8 m g square, okay, n minus 1 by 4 whole square pi square h cut square. Let's look at the options and solution. What it is equals to? Alpha into n minus 1 by 4 pi square h cut square into g. So we can write it E n is equals to 9 by 8 m n minus 1 by 4 square pi square h cut square into g square. 9 by 8 mg, let's say हम g रख देते हैं, एक और g यहाँ पे. So 9 by 8 mg n minus 1 by 4 whole square pi square h cut square into g. So it is matching with option C, right? One mistake we have done, I think, is this one, e to the power half, and e, this becomes e to the power 3 by 2, right? That is why it is not matching with the option. So if you take a square, it becomes e cube. So it is en cube. So if you compare it, alpha n minus 1 by 4 whole square pi square h cut square into g. So alpha is equals to 9 by 8 mg. That is matching with option C. So I hope you have understood. Look, I have tried to make this topic as easy as possible. If you go through books, you will find it very difficult, okay, to decode. But I have tried to make it very much clear, step by step. So I think this lecture is enough to solve any question from WKB approximation. Are you getting confidence? after attending the session? Are you getting confident that you will be able to solve question? Any question from WKB? Murli, Karthik? Harry is not attending regularly. What happens to her? Look, live class has special importance. If you watch the recording, you don't get that feeling. Okay, when you attend live, you think you are activating your thought process. If you watching the recording, you will maybe play it on 2x or 1.5x, or you will just skip it. So you will not get this thing effectively. Okay, got full confidence, very good. Okay, so this topic is also over. This was one of the advanced topic, and only few topics are left. Then our course will be completed on this quantum mechanics. Okay, bye bye, take care, see you in the next class.